Hello everyone, welcome to my channel. I am making a lecture series on quantum mechanics. This is the first lecture. I will be following the book Principles of Quantum Mechanics by R. Shankar. I am making this video series for myself and uploading it on YouTube so that others can see it if they are interested, and if I explain something wrong, so they can tell me about it. I can understand things better from that mistakes. I believe teaching is the best way to learn something. I previously studied quantum mechanics, but I forgot everything. Not everything, but forgot many things. So I am making this video series for myself so that in future I can look back what I studied. So let's start. Principle of quantum mechanics. The first chapter of this book is called Mathematical Introduction. In this chapter we will learn what are the mathematical tools and mathematical ideas we need for quantum mechanics actually. So let's start. The first topic of our chapter is linear vector spaces. We all know what vectors are. Something with a magnitude and a direction. We can represent it geometrically by an arrow, and we can represent it by like something A and a arrow over it. And then we also know the rules of vectors addition and multiplication of vectors by scalars. We know if we have some vector A and another vector B, if we sum A plus B, that will be equal to B plus A. We know that. We also know some rules of multiplication like this. So we want to generalize vectors more. By generalize these rules, we can draw a set of basic features or axiom and say that any set of objects obeying the same forms a linear vector space, and we will find them useful to us later in our course. So mathematician has made a list of properties that can be associated with a vector space. Let's see those properties. So our first definition, one, will define a vector space, linear vector space, a linear vector space V, let's write it like this, V is a collection of objects. These are the objects these objects called vectors for which there exists some rules, and the rules are: number one, a definite rule for forming the vector sum. A definite rule for forming the vector sum, denoted by this: v vector plus w vector. And that will also have a multiplication rule, and that is defined by a definite rule for multiplication by scalars. A, B, etc. denoted A multiplied V with the following features. So a linear vector space will be a collection of objects called vectors, and that those vectors will follow certain rules, and there will be a definition of a sum called vector sum, and there will be a definition or rule of multiplication by scalars, and this sum and summation and multiplications will follow some rules. So we'll see what are the rules. First rule is, if we sum any two vectors, it will produce a new vector, and that vector will also be an element of our vector space. Second rule is scalar multiplication is distributive. What does this mean? If I sum two vectors and then multiply it with any scalar, this will be equal to multiplication of individual vectors with their scalar and summation. Third rule is scalar multiplication is distributed in the scalars also. That means a plus b into any vector will be a into v plus b into v. Scalar multiplication will be associative. That means the order will not matter in multiplication rule. Fifth rule is addition is commutative. That means the order of the addition will not matter in vector sum. Addition is associative. Again, there exists a vector called null vector that is denoted by this, and this null vector will obey this rule. If I sum any vector with null vector, I will get the vector back. And the final axiom or rule will be there also exists a inverse vector. Let's say if v exists in our linear vector space, then there will also exist a vector minus v such that v plus minus v will be 0. So these 10 rules are the rules of linear vector space. So what is a linear vector space? Linear vector space is a collection of objects. Those objects are called vectors, where there is a rule for vector sum and there is a rule for multiplication by scalars. And those vector sum and multiplication rules follow these 10 rules. What are the 10 rules? If I sum any two vectors, it will produce another vector that will also be element of our vector space. The order of the multiplication and the order of the sum does not matter. There exists a null vector denoted by 0, that summation of null vector with any vector gives us the vector back. And there also exists a inverse vector for every vector in our vector space, that v plus that inverse vector plus any vector gives us 0 vector or null vector. These are the rules or axiom for linear vector space. We will appreciate this definition throughout our course. Right now they can be same like abstract. Okay. Second definition, definition 2, the numbers, the scalar numbers a, b are called the field over which the vector space is defined. So the scalar, the numbers we multiplied with vectors A, B, C, etc. are called the field over which the vector space is defined. If the numbers are scalar, then we say we have a real vector space, and if the numbers are complex, we have a complex vector space. If the numbers are real numbers, we have a real vector space, and if the numbers are complex number, we have a complex vector space. The vectors themselves are neither real nor complex. The adjective applies only to the scalars. Right? We cannot say this vector is real or complex. Okay. We can only say A, B, C, they are real or complex. Okay, vectors are not real or not complex. This adjective only apply to the A, B, C, etc. So from the axioms of linear vector space, from definition 1, we can come to conclusion about certain rules, or that is, if I multiply 0 with any vector, I will get the null vector back, and the inverse vector is nothing but minus the vector. And minus v is the unique additive inverse of v. So these are my two definitions for linear vector space. Let's do a problem. Let's consider a set like this, A, B, C, and where A, B, C are real numbers. The addition and the multiplication of this set is defined as follows. If you have A, B, C and another D, E, F, the sum is defined by this, and the multiplication rule is defined by this. Alpha is any number, B, C is alpha A, alpha B and alpha C. This multiplication rule and summation rule are defined for this vector space or vector space. So our question is, what is the null vector in this scenario and inverse of ABC? As from our axioms, we know any vector plus null vector must come, the summation will give us the vector back. So by the definition of this summation, we can see, if I sum it with 0, 0 and 0, I'll get back A plus 0, B plus 0 and C plus 0. It will give me A, B, C again. So for this vector space, the null vector is 0, 0 and 0. And the inverse vector will be of ABC, will be minus A, minus B and minus C, as a b c plus minus a minus b minus c is 0 comma 0 and 0. So from the axiom itself we can say in this vector space this is our null vector and this is our inverse vector of ABC. Another problem is we have to show that A B1 this set does not do not form a vector space. So it is pretty easy. If we multiply this any vector with a scalar a b1, the given our given multiplication rule said this will give us alpha a, alpha b and alpha, which is not a part of our vector space, because our vector space, the vectors of our vector space have this form. So this set AB1 do not form a vector space. Okay. You might notice that we are using a new notation for vectors, right? We are not using the usual arrow sign over a letter to denote vectors. We're using a new notation like this. This is called Ket V, and we will come back to this why this is called Ket V. We are following actually Dirac notation of vectors. We are not writing this form so that we can go away from the limited concept of the vector as an arrow. We'll see in our course that typical vectors do not always cannot be always represented through a arrow. That's why we are using this notation. Also, from analyzing our definition or axioms from linear vector space, we can see that the arrows we draw to represent vectors geometrically, they all form a vector space. Also, arrows have magnitudes and direction, but arrows have magnitudes and direction, and the magnitudes was the length and the direction is given by this arrow. Members of vector space do not need to have those. We will see. Example of such vector space is 2 into 2 matrix, 2 matrix. Like if you have some vector a, b, c, d, and another one like e, f, g, h, we know how to multiply two matrices and how to sum two matrices and how to multiply matrices by scalar. So if you sum these two, you will get a plus e, b plus f, c plus g, and d plus h. This is also a 2 by 2 matrix. So 2 by 2 matrices also form a vector space. Two by two matrices also form a vector space. but we cannot assign a magnitude or direction with matrices. So in our definition of vector space and vectors, typically vectors don't have magnitude and direction. So these are our definition for vector space and vector. Now consider a linear relation of the form like this. AI, these are scalars, numbers, and these are vectors. Let's suppose this is our equation 1. Let's suppose you have this equation where you are multiplying multiple vectors by scalars, and if you do the sum you are getting a null vector. From this equation we will define another thing. So this will be our definition 3. The set of vectors is said to be linearly independent if the only such linear relation as equation 1 is the trivial one with all AI equal to 0. If the set of vectors is not linearly independent, we say they are linearly dependent. So what is it saying us? If equation number 1 is satisfied only by all the AIs are 0, then the vectors I vectors will be called linearly independent. If any other way it is possible to get 0 without all the AIs being 0, then the set of vectors will be called linearly dependent. Let's understand this definition by our usual arrow vectors. If you have a vector that is in the direction upward and another vector direction of horizontal direction and vertical direction, I can let's write them through capital B, and this let's write them through capital A. If I write this linear combination of these two vectors and I want to find null vector, that is just a point, there is no magnitude of null vector. It is only possible if both A and B are 0. So these two vectors, we'll call these two vectors are linearly independent. And it is also true for these two vectors, A and B. Again, this can be 0 only if A and B are 0. If the set of vectors is linearly dependent, it is possible to write any member of the set in terms of the others. Let us say A3 is 0, then we could write not 3 to n minus ai a3i. If they are dependent, we can write this. So let's see another example. Let's say this is my one vector, and this is another vector 2. They are obviously linearly independent. And let's see a vector 3. From the starting point, let's go in the parallel direction of 1 and in the direction 2. From here we can see if we have 2 1 and 1 2, we can form 3. So here 1 and 2 are linearly independent vector, but 3 is not. 1 2 and 3 is not a linearly independent vector set. Let's do a exercise or problem so that we can understand this linear independency or dependency better. Let's say you have 3 element of 2 by 2 matrices. One element is given by this, one element is given by this, and one element is given by this. The question is here, the problem is, are they linearly independent? Are they linearly independent? So for them to become linearly independent, what will be the solution? We know if the solution of this equation is only all ai's are 0, then they are linearly independent, right? So let's write it. Here n is 3 because we have only 3 elements. So let's write a1 with the first one, and the first one is 0 1 0 0, plus a2 with the second one it is 1 1 0 1, and the third one is -2 -1 0 -2 equal to 0. Now we'll solve this and we'll find out the values of a1, a2 and a3. If they all are zeros, then these three vectors are linearly independent. If they all are not zero, these three vectors are linearly dependent. So we all know how to do matrix multiplication and matrix sum. So from there we will get these equations and this equation. So we have three unknown, only two solutions, so they will give us multiple solutions. So it is not necessary to all of them to be zero. So from here we can come to this conclusion that these three matrices are linearly dependent. This is linearly dependency. So let's go to definition 4. A vector space has dimension n if it can accommodate a maximum of n linearly independent vectors. It will be denoted by VNR. Here R if the field is if the field is scalar, if the field is real, and VNR if the field is real, and VNC if the field is complex. So if my vector space has three independent vectors, then it will have 3 dimension. An easy example is our 3D world, where we have actually determined what force, velocity, displacement, etc. Those vector space has 3 independent vectors, namely I cap, j cap, and k cap. So those vector space has 3 dimension. We can also give a example of a 4-dimensional vector space. Example of a 4-dimensional vector space. if you take any 2 by 2 matrices, you can write them like this. Like this. These 4 vectors we can easily check. These 4 matrices are all linearly independent. We cannot represent one with help of the others. So as there are 4 independent vectors, this vector space is called a 4-dimensional vector space. From this definition, we can come to our theorem 1. Any vector, let's say ket v, in an n-dimensional space. Let's say our vector is an element of a n-dimensional vector space, can be written as a linear combination of n linearly independent vectors. One to n. Any vector of our vector space can be represented as linear combination of n linearly independent vectors. How can we know this theorem is true? Right? If there were any vector for which this were not possible, right? If we cannot write them as a summation of linear combination of n independent vectors, that means that vector would also join the given set of vectors and form a set of n plus 1 linearly independent set, right? Linearly independent vectors, which is not possible because our vector space is n-dimensional space. So this theorem is true actually. After that, our definition 5. A set of n linearly independent vectors in an n-dimensional space is called a basis. Right, if we take any vector and write it through them like this, linear combination of n multiple vectors, these I vectors, right, these I vectors form a basis. This is called a basis. If we want to give an easy example, that example would be of our three-dimensional vectors. For our three-dimensional vectors, our basis was I cap, j cap, and k cap. After definition 5, there will be definition 6. The coefficients of expansion vi of a vector in terms of a linearly independent basis are called the components of the vector in that basis. These VIs are called components in that basis. What does it mean? Let's say you have a vector, a arrow vector like this, and you are representing this vector with, let's say, 1 this and 1 this, right? Let's say this is your vector v. So in this basis system, this 1 and 2 are linearly independent. In this basis system, your v will be 1 plus 2. Okay, and if I take again like this is our v, and let's say we are getting this vector by adding a one vector that is given by this and another vector that is given by this. This is called 1, so this is also a 1, and this vector is 2. So this 1 and 2 also are linearly independent. In this system, I can write v as 2i plus 2. So for this basis, here my components are 1 and 1, and for this basis my components are 2 and 1. These are called components of our vectors. From these definitions, we can come to our theorem 2. The expansion of a vector in a basis is unique. That is saying that in this basis system, we cannot express our vector or expand our vector in any other ways. Also, in this basis system, we cannot expand our vector in any other ways. It's a easy proof. It has a easy proof. Let's say the proof of this. The proof of this theorem. let's say I am representing my vector like this, and I can also represent my vector say in the same basis system with different components, right? If I subtract this and from this, I will get a zero vector and summation of I vi minus vi prime into my basis vectors. From this, we conclude that vi and vi prime must be equal. Hence, our theorem is proved. We can, in a basis, we cannot expand our vector in any other different ways. From these theorems and definitions, some things are very easy to follow. Like if I have v written like sum vi I, and if I have another vector element w written like this, if I sum those vectors, I just need to sum their components. So our rule is to add two vectors, add their components. And this is the multiplication rule. So easy rule: to multiply a vector by a scalar, multiply all its component by the scalar. So these are the rules we also saw in our three-dimensional vectors like displacements, velocity, acceleration, etc., etc. So this covers our definition of linear vector space, and what is a linear vector space, and what are vectors, and what rules they follows. It was carefully, these rules or axioms were carefully chosen by mathematicians that we will appreciate later. Now they will seem abstract definition, but as we go further and further into quantum mechanics, we will see these definitions or these theorems will help us a lot. So I think this is the time where I should end my video. If you like this video, please subscribe to my channel, and if you have any suggestion, please drop a comment below.